Hello, my name is Jordan Tu, and I will be demonstrating the ICP Deep Learning 4 over the topic of convolutional neural networks. So today we're going to be working with CIFAR-10. It's an image dataset that contains, I think, over 60,000 images, I believe, based off of 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. And in our software today, we're going to try and create a model that will um, try to predict what the image is going to be based off of that image dataset. So over here, we are creating our sequential model, and our sequential model will include multiple layers of CNNs or convolutional neural networks. One of the advantages that we have with using CNN is that it is useful for recognizing spatial relation between features in the image, which compared to traditional neural networks is not considered. And it is very useful for working with large, larger images. In the dataset CIFAR-10, we are using 32 by 32 pixel images that are in color, RGB. So uh, when trying to extract features from that and running it through our neural network, having to run the model through over millions of individual um, points or pixels can become more taxing to and time consuming when trying to run our model as compared to CNNs where we're able to essentially reduce the those features to help speed up computation. So here we are creating multiple CNN layers. I won't explain each of them since they're specified through the lesson plan, but we're creating convolutional input layer with 32 features with a size of 3 by 3 and a rectifier, the ReLU rectifier activation function. The input shape is referring to RGB, um, the color of the images in the dataset, and then 32 by 32 for the pixel size. And then we create a dropout layer after that. Um, so we create multiple convolutional CNN neural networks here. And then here we are using max pooling. So the benefit of max pooling is it allows us to reduce the size of the layer to help speed up computation and lets us also retain certain robust features that have run through the model at that point. Um, yes, so we use max pooling, and then after we do that, it flattens the layer, dropout layer. And once we have, after that point, we are using fully connected layers. In this situation, in this case, 1024 units, 512, um, with the ReLU activator function that connects each of those neural networks together. And then we finally connected to our final output layer with a softmax activation function. Um, this will have 10 units for the output, which indicates the 10 potential output classes that I mentioned earlier, the 10 different categories that what an image could be in the data sets. And then here we compile the model, and then we fit the model, and then we run a final evaluation on that model. Here I am running the code, And this type of computation takes significant amounts of time, depending on how many epochs, how many times it runs through the model, that sort of thing. So I have a screenshot over here that will show the different results of the data. So the original code that was specified gave us a accuracy of 42.25%. And the new model that we created, we actually had a loss of accuracy of 27.93%. So the accuracy will definitely improve as the longer you run the model through if we have multiple epochs. Over here we have the inference 3. So in our code over here, we had, as this is our model currently running, but in our model we wanted to make a prediction on the first 4 images of the image dataset, and the prediction was 3, which should be a cat, and once we run it through, it makes the prediction of 3. I don't know where that image went. Here it is. Image of 3 of our prediction that it is a cat. And that is the demonstration of the code. Unfortunately, I was unable to get TensorFlow to work properly with my dataset, but anyways, thank you so much, and that's it.